Hey guys, and welcome back to another video on the channel. In this video we're going to be going over just a little proof by induction. So today we're going to be proving this statement here. So 1 plus 3 plus, what was it, 5 plus dot 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 2n minus 1 is equal to n squared. Now what this is, and n belongs between only the positive integers, okay? Now what this statement here is saying, it's pretty much saying, alright, that this general rule is basically equivalent to this. So the way we have to prove this is true is, alright, it's by induction. So induction basically means, alright, true for n equals 1, n equals k, and n equals k plus 1. So to start off we go, alright, see if true for n equals 1. So if we put n equals 1 in here, we're going to have 2 times by 1 minus 1. What's that going to give us? That's going to give us 2 minus 1, so that's going to be 1. And if we put in, that's also, alright, 1 squared, that's also going to be 1. So left hand side is equal to the right hand side. Okay? So that's the first bit true. Now we have to assume it's true. So we have to assume this entire statement is true. And basically we've got to say, alright, assume true and let n equal k. Now you're probably wondering, why do you have to just change this variable? Well, we start off by saying, alright, this whole thing works when n equals that. So we've got to assume that it works for pretty much any number. So we generalize it by saying k, and we have to define k as an integer, because this formula only works for positive integers. So we say, let n equal k for k belongs to the positive integers, okay? And then we substitute k into here. So we have 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is equal to k squared, okay? Alright, so we've basically assumed it's true for any integer. So now we have to assume it's true for the integer after this integer. So that means k plus 1. So assume true for k plus 1. Now we don't have to write anything belongs because we've already defined k as k belongs between these integers here. So assume true for k plus 1. So in this sequence here, we're basically saying, alright, how does this sequence actually come about? So if you notice, if you put n equals 1, that gives you this here, and that's the first term here. If you put n equals 2, what does that give you? That's going to give you pretty much the next term, isn't it? It's going to give you 3, because if you put 2 in there, that's going to give you 4 minus 1 is 3. So this is like a general rule for this sum here, okay? So what we're doing when we go k plus 1, we have to go, alright, 1 plus 3 plus 5 plus dot 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 plus 2k minus 1. Then we go plus, and then put the k plus 1 in here. So the sum after it. So 2 of k plus 1 minus 1 is equal to k plus 1 all squared. Now the induction bit is basically, alright, we have to recognize that this entire bit here is actually this bit up here. And that's equivalent to k squared. So we can make the substitution that k squared is that bit there. So we substitute that in, and we're going to go plus, alright, 2k, distribute this here, plus 2 minus 1 is equal to k plus 1 all squared, okay? Now simplifying this gives you k squared plus 2k plus 1 is equal to k squared plus 1. And you notice this is actually a perfect squared. So this here is actually equivalent to k plus 1 all squared, which is equal to our right hand side. So therefore left hand side is equal to the right hand side. Therefore this statement is true for all integers, because we basically worked out every general case. So we worked out, alright, true for the most basic case, n equals 1, true for n equals k, where k could be any integer as specified here, and then assume true for the integer after k, so k plus 1. And then, yep, make that substitution, and we've proved it. So this statement is true for all integers, well, that are positive. Alright, thank you for watching.